Okay, this is a ballistic pendulum problem. So we have a mass, M, big M, sitting on a table and attached to a cord which is attached to a ceiling. A bullet comes in with some velocity V right before it hits the mass, and comes in at a height h above the ground, hits the mass and exits. And we're going to consider the collision time to be very, very, very short so that the bullet exits before the mass big M moves, okay? And then the bullet goes out and then falls down on the ground. And then the mass swings up to a height h prime. Should be the other way around. Something like this, okay? We'll have a better drawing down there. So this is how the setup is, okay? Bullet comes in, hits a mass, it exits and falls down on the ground. The mass swings up to a height h prime. Now we're going to answer some questions. So let's look. Here's the write-up of the problem, okay? And we need to get answers in terms of the initial velocity of the bullet, the mass m, big mass M, the height h, and gravity, okay? So we're given that the block swings to a height h over 8. And the little mass, the mass of the bullet, is the mass of the block over 25. Okay? So with what speed does the bullet strike the ground after it leaves the block? So let's draw a little drawing right here. So for part A, so here's the block. Right before it starts swinging, the bullet has penetrated already and is leaving right now. So here's the mass of the bullet, the velocity, and it's going to go down. Here's the leg of the table and fall at distance h. Okay. Now, whether we're using kinematics or conservation of energy, we need to know this velocity v. Okay. And it's purely horizontal. Okay. So where are we going to get this velocity from? Well, before we get to this point, the bullet had a collision. Again, the key point is collision with the block, and the block swung up to a given height, h prime. So maybe that information can be used to give us the velocity right after the collision, which then we could use kinematics or conservation of energy, compute the speed as it hits over here. Just a magnitude, right? No direction, just a magnitude. So let's see what happened during the collision, okay? So here's the situation right before the collision. And here's so the bullet's coming in with a mass m and the velocity v. The big mass m is not moving, so its big velocity is 0. And after the collision, both of them, the bullet has exited already with some mass m and v prime, small v prime, but the big mass m started to swing with a mass capital V prime, okay? And this is after the collision. Now, obviously, the collision is not elastic. We do not know the energy expenditure for the bullet to enter, deform, heat, sound, all of that. All we know is that all the forces are internal, and we can use conservation of momentum. So momentum before equals momentum after. Obviously, since we're taking everything to be positive to the right. So initially, before, we had two objects. The ones that are moving have momentum. So capital M has no momentum because its velocity is 0, but the bullet has momentum, and its momentum is mv. After, what was moving? Both the capital M, or the big block, was moving, and the bullet was moving both to the right. So both momenta are positive. And here's the momentum of the block plus the momentum of the bullet. I'm looking for V prime. So it looks like I'm almost there. I know this, right? I know M and V because M is given in terms of big M, right? Right here. Here's big M, I know it. Here's little m, I know it. The only thing I don't know is V prime. How do I get V prime? Now, we go to the second piece of information that was given to us about the block. So here's the block right after the collision. The bullet has exited. So this is right after the collision. And then the block then swings to a height h prime. Okay? I mean, it starts moving with capital V prime, and then that energy that it has makes it swing up to a height h prime. Okay? Maybe we can use conservation of energy to get what capital V prime is. So let's do it. Here's the initial. Here's the final. Now, we're going to take potential energy to be zero right here. So here's potential energy equals zero at this level. So now we ask ourselves, here's energy initial equals energy final. All right, what kind of energy did we have initial? The big block was at the potential energy equals zero line. So there's no potential energy for the, again, remember, it's a potential energy difference. So we're taking the zero to be at the lowest level. So it has no potential energy, but it's moving with velocity V prime. So it has kinetic energy. And then final, when it gets up to a height h prime, it stops. So it has no kinetic energy, and it's at a height h prime above what we chose to be the zero reference line. So it has some kind of a potential energy. Fine. So kinetic energy is 1/2 m v prime squared. Potential energy is mgh prime. And remember, h prime is h over 8. Right? We're going to plug those in here in just a little bit. So I know what v prime squared is now. So the m's cancel. So v prime is the square root of 2gh prime, which is the square root of 2gh over 8, which is the square root of gh over 4, or 1/2 the square root of gh. Here's capital V prime. So now I can take this and plug it in here, and I can get what little v prime is. So let's do that. And I'm going to substitute the mass in there. So here, for this one, I'm going to put m over 25 v. I'm going to bring this over here, minus m. V prime now is 1/2 square root of gh equals m over 25 v prime. I'm substituting for little m as capital M over 25. Obviously, the m's cancel out. So I know what v prime is. I multiply by 25 throughout. So I have v prime equals v minus 25 over 2 square root of gh. And in a way, it's good because this tells us that the velocity upon exit is smaller than the velocity upon entrance, right? It's going to lose some velocity. All right. Now that we know what v prime is, So what's happening to the bullet? Here's the bullet. It exits the block at velocity v prime and drops a height of h. So what's the speed over here? Okay. So again, this is its initial position. This is its final position. We are going to take the potential energy equals 0 line over here. So now we can use conservation of energy. Use energy conservation. The energy initial at point I up here must equal the energy final. There's no loss to friction or anything like that. So what kind of energy do we have initial? Again, we have to go through our list of energies in our mind. We have potential, we have kinetic, we have potential, again, due to gravity and due to spring, we have friction, we have thrust, all of those. None of those are there. The only thing we have there is that right now is gravity and kinetic energy. So this thing is above the 0 line, the potential energy 0. So it has potential energy. So we have some kind of potential energy initial, and it's moving. So we have kinetic energy initial. And that's all the initial kinetic energies we have. Final, well, right before it hits the ground, it's moving. So we have some kinetic energy final, but it's at the 0 potential energy line. So there's no gravitational potential. So let's plug them in. mgh for the potential energy initial plus 1/2 mv prime squared equals, here let's assume it's moving at say v double prime will be 1/2 mv double prime squared. So m's cancel out, multiply by 2 throughout, so v double prime squared equals 2gh plus v prime squared, and here's v prime squared, v minus 25 over 2 square root of gh squared. So v double prime is going to be the square root of that. And you could keep it like this. You don't need to actually expand this. This does not need to be expanded. You can keep it like that. Okay? And here's the velocity right before it hits the ground. And it's in terms, well, obviously it's not going to have mass in it, right? But it's in terms of GH and little v, all the information that was given initially about the problem. Now, part B, they want to know how far does it fall away from the table. So we want to know this x. So for part B, let's write down what the equation is and see what we know and what we don't know. All right, in kinematics and projectile motion, there's no acceleration horizontally. So the initial velocity is the final velocity, is the velocity at any point in its trajectory, horizontal, right? So the horizontal velocity is the same. So x then becomes x0 plus v prime t. And here is the v prime. At any point, the velocity horizontal is the same. So there's no acceleration in the x. Now, if we choose our axis, where this is our 0 for x and our 0 for y, then x0 can be taken to be 0. So x equals, what is v prime? V minus 25 over 2 square root of gh times t. Well, the only unknown here is t. We need to find t. And just like with any projectile motion, 2D motion, the motion in the y and the motion in the x are connected by time. So let's see if we can get time from the y motion. Let's see what's going on in the y motion. So now let's look at the y motion. This is X motion, no acceleration in X. Y motion, let's draw it. It's always good to have a little drawing. So here's, so as the bullet goes this way, it's dropping. So the bullet is going to drop horizontally a distance, vertically a distance h, under the influence of gravity, okay? So if we take our axis to be like this, for the y and the x, then we can use this equation. Y is y0 plus v0 in the y, t, plus 1/2 the acceleration in the y, t squared. Well, let's see. When the bullet hits the ground, y is 0. Y0, what's the initial position of the bullet? It's h. I have no initial velocity in the y direction. And I have the acceleration in the y. Since I chose my axis this way, gravity is down, so it would be negative g times t squared. So rearrange, bring the h over, multiply by 2, divide by negative g. So t squared will be 2h over g. So t, so 2h over g. Okay? So now that I know what t is, I plug it up here for x. So x equals, I plug t into the x equation. So the x equation has v minus 2 over 25 over 2, square root of gh times 2h over g under the square root. And that is the distance x in terms of given quantities, hg and v. Okay? So we used kinematics, used conservation of energy twice, and we used conservation of momentum way up here during the collision, right there. So that's a good, well-rounded problem. I hope you enjoyed. All right, thanks.